Hello everyone, welcome to Tech Talk session number 40. Today we're talking about the ABB Ultra Fast Earthing Switch, UFES. Today's presentation, we're going to have Martin Kropf with us from ABB. He's out of Germany, so he's coming a long ways to talk to us over Teams. So don't forget, in NEPSI Tech Talk session 5, we talked about arc flash hazard mitigation and ways to reduce the hazards associated with arc flash events within metal closed capacitor banks and harmonic filter banks. One of those techniques was active arc flash mitigation, and the device that we use to perform that function is the ABB Ultra Fast Earthing Switch. So today we're going to have a presentation with Martin of ABB, and we're also going to do some video presentations. We have exactly, I think, 3 or 4 videos that we're going to show. So Martin, welcome to the Tech Talk.
Well, wonderful good evening from Germany. Thanks, Paul, for having me. It's a pleasure to be on.
Yes.
As introduced, I'm Martin Kropf, working in Germany, in Ratingen, let's say, close to Düsseldorf, where we from ABB are producing key components for medium voltage. You see some of me around. These are mainly the short circuit products, and one of them I'm really looking forward to introduce to you and discuss with you, and also answering questions today. So looking forward to our session.
Yeah, so he brings up a good point. Don't forget to ask questions in the chat box at any point in time. Today we are taking questions as we proceed along the presentation, so please ask questions anytime. We also have Kansu in the background, who's an applications engineer with ABB, and she could pop on also for the questions that Martin can answer. Also, don't forget about the, and PDH contact hours. Email Matt or myself at the end of this presentation, and we will get you a contact certificate, and we're going to give you a code at the end, okay? So send us the email if you want that certificate. So Martin, why don't you just introduce what you do real quick, ABB, then you can get on. Oh, there was one last thing. We wanted to show a video first, and I should do that. So let's get on with the video of an arc flash event. This actually occurred with a piece of equipment, a NEPSI equipment, and yes, even NEPSI once in a while might experience some type of catastrophic failure.
So what happened there, Paul?
Yeah, well, you know, it was a failure in the incoming compartment of an enclosure located over here, and I don't think you can see my mouse, you can see that the door does about a triple flip, maybe 3 or 4, 5, 6. So just kind of watch how it kind of flies through the air. So it's spinning through the air. That door weighs about 125 pounds. It was welded on. It's a 3-point welded hinge. Our hinges are rated 125 pounds each, and it had a 3-point latching handle, and you can kind of see where it's just spinning through the air. And when it actually finally does land, check out the door is bent upward, and we use 11 gauge steel. So it's a substantial amount of force. This failure ended up being in the incoming compartment. It was a component failure. And a lot of things with electrical equipment can happen. I mean, things do fail. So it's important that you consider, well, what are those costs and what are the hazards associated with the people, but then also the equipment itself. So just as an introduction to the equipment, into the what we're talking about today.
Exactly. I mean, it was also shown, I mean, in the video very, very effectively. I mean, I think this application, there is a fence around. We have seen it, right? It's quite, I think, somewhere outside of a city area. There was a lot of fire, was smoke, probably also toxic gases and so on. So it's really a disaster if something like this happens. So, yeah, exactly.
All right. So today we're talking about the ultra fast earthing switch, the UFES system.
How to avoid this, let's say, exactly. Very good. So I've prepared some slides so we can have maybe a quick look on this, if you agree. Yeah, very good. I mean, let me start off, and well, you have already shown that the reality, Paul, in the video, but I prepared, let's say, here a slide. How would a world look like without this, without internal arcs, if we don't have to take care of this let's say, challenge? First of all, what we see here, we have definitely, the first point is we have greatly increased operator safety. I mean, this is really the most important thing. And if we would have a world without internal arcs, we could really have, let's say, this peace of mind. We then, but also after safety, we also have, as you see here, a drastic reduction in, let's say, downtimes on the one hand side, as we see here, but also drastic reduction in repair, warranty, and also consequential costs. So it's really, if we don't have internal arcs, we don't have, let's say, inside application like switchgear or, let's say, capacitor bank application, where we really have, let's say, damage of equipment. So we have a power off, we have to repair things. And also if time is really money, we would like to be, this is great, without internal arcs, you then, let's say, you don't have this issue. And last but not least is here, one important thing is, actually, we don't need to consider this internal arc challenge if we have custom gear, if we have, let's say, designed to order things, which are, let's say, not easy to test, because you cannot just test every design to order thing, because then you have to build it twice. And last but not least, also the pressure relief. I mean, you have seen it in the video. Well, this is a challenge, really, because you might have areas where it's really a challenge to have such an event, if you have a public area, or also an area where there is no pressure relief possible. Let's imagine of a metro system or something, or a mine or whatever. So unfortunately, this is not the real world. We have internal arcs, and let's first have a quick look why they happen. I mean, we as ABB, we really try everything to avoid internal arcs, first of all. But there are mainly three, let's say, areas which you have on this slide, where we have, let's say, the reasons why those things really happen. First of all, human-related causes. We are training people, we have rules, we have interlocks, everything to avoid internal arcs, but still it happens. It happens that people are not following the rules because they are in a hurry. They think that the cable compartment in a switchboard or in an application is not live, and then they start to vacuum clean a cable compartment, but it was live. This happened. We have also, let's say, installation faults. We do some failures. We forget the tool when we're making a maintenance. So this is human-related causes, and this is something which is really, let's say, a challenge what we see. And also what I would like to highlight, human-related causes always means that also most of the time humans are close to switchboards, to the application, and this brings the safety issue as well. Then we have technical related causes, aging, wear, defective devices, over voltage, over temperature, and as well as environmental causes, which we have, so moisture, dirt, corrosion. We have animals sometimes in the switchboard, and are all reasons which then cause an internal arc. Looking shortly to the timing, I prepared this here to just show you what energy level we really have in over time if we are facing an internal arc. And there are actually, let's look at the conventional protection, what we have normally installed, which means we have a standard relay, first of all measuring current, and then it sees, oh, there is an overcurrent, oh, what it is, it's probably an internal arc, okay, I have to switch off a breaker, it sends a signal to the breaker. The breaker then decides, okay, let's open, it opens, and then we have an interruption. This, if you are, let's say, fast on this, with this combination, you are above 100 milliseconds. You are maybe also, if you have an upstream breaker which you trip, you are maybe also more than 200, 300 milliseconds, and then you interrupt the current. But then, as you see here in the slide, we actually are in a range of cable fire, copper fire, steel fire maybe. So the damage is really heavy. We have, if somebody is involved directly, we have heavy injuries of the personnel, and we have really dramatic consequences. So there are actually two steps where you can improve. First step is we can try to be faster in detection. So we choose a fast protection relay. This is then definitely helping, because we are having a relay in place which is optimized with light sensors, for instance, to really be very fast detecting the internal arc. Relay times in that area are 2 to 3 milliseconds then. So after 2 to 3 milliseconds, you know it's an internal arc, and then you trip the breaker. You trip a breaker, which is opening again. It's maybe a mechanical device. Normally, there are some magnetic devices on the market. We from ABB, we love breakers. We have our great breakers like the VD4 in IEC or the MVAG or ADVAG in the ANSI world. But the breaker is itself a very standardized device. I mean, it is fulfilling today. It's fulfilling its need. It's highly standardized as well, and so it's not that it's easy to optimize that breaker because it's always a payoff. I mean, you can make it faster, but a breaker today, 50 to 80 milliseconds opening time, roughly, a medium voltage breaker. So to bring this really down, it's really hard, and it will affect the performance of the breaker. It would then not operate, let's say, 10,000 time maintenance free. So we will not be able to change the breaker because this is widely used and accepted technology. So you see here now, fast detection, great, 2.5 milliseconds, for instance, and the breaker takes then another 50 to 80 milliseconds. So we have to find another way, and this we have done with the ultra-fast earthing switch, and we are down at 4 milliseconds. And this means really, as it's written here, actually no consequences to affect it. To make it short, you can clean away a fault. And this is the key thing. How it's going to work, and I would like to show you this to you shortly on this slide. You see here, let's say let's assume it's a bus bar here. It's an incoming or a feeding. Normally in a switchboard, this is an incoming panel, and then we have here, let's say, the system installed. We have here the UFES, the ultra-fast earthing switch, PSE. It's the primary switching element, which is actually an isolator in normal mode, so it's open. We have the detection electronic, we have the tripping electronic. These are in place here. And then what we have here in this is number one, we have, let's say, an internal arc happening here, let's assume on the bus bar. And we have this internal arc burning. So what we are doing, we have, let's say, first of all, in step number 2, we are detecting by light. Here you have the symbol of a light sensor. And we are detecting by current. We do recommend to have this logical and connected, means we are detecting an internal arc with light and current. Since only light, we can do that as well. We can do light or current. It's also possible, or only current or only light. This is both possible, but we recommend the logical and. Why? Because if we have the only light, we have, let's say, the risk that maybe at the commissioning of the switchboard, the customer is happy about it. He would like to make a picture. He uses a bit of strong flash, and then we have the trip, because a strong arc flash of a camera can really trip also the light sensors. If we go only current, we have the issue, it's possible, but then it's just clear that we are also tripping if there is an external fault. If there is an external fault somewhere, not an internal arc, we are also tripping, since the tripping criteria of current might be fulfilled. And this could be done if we want to do this, or if we just want to focus on the internal arc. As I said, it would make sense to have logical and. So in step number 2, we have understood it's an internal arc. The detection unit in step number 3 then gives a signal. Well, this is done also in step number 2, but then in step number 3, we are giving the tripping signal to the primary switching element, and as well, optionally, if we want to do this, otherwise we have maybe a protection relay system aside, which is doing this. We are also giving a tripping signal at the circuit breaker here. Step number 4 is the essential one. We are actually then closing the earthing switch, and in that, when this is happening, we are, let's say, shutting off the arc. And how we are doing this? We are giving the current to ground a more attractive way. And this is via a 3-phase solid earth connection via the primary switching element. And the key topic is the timing. We are in step number 4 in less than 4 milliseconds. And then it's actually not that important anymore between step number 4 and step number 5. How long does it take? Because the current is not creating any damage anymore after step number 4. And this is actually how we are working. How we are working technically, shortly here, what we are having in the primary switching element, actually we are having here a vacuum let's say, interrupter inside. This is the core, since we have to isolate most of the time. So we are making very good isolation. Once we are having, let's say, we are detecting the internal arc, we are shooting in, let's say, this bolt you see here. The energy is coming from this device down here, which is actually a very well-known device. It's a microgas generator. It's very similar to the one which you may know, but I hope that you don't know. It's actually the one which you have your front in your face every day. It's very similar to the airbag mechanism which is used in the automotive industry. So we are shooting this in, and then it looks like this at the end. You have here some figures. What is the size of this, let's say, primary switching element? We are having, let's say, the closing in around 1.5 milliseconds, and then the thing is closed, and then it looks like this on the right-hand side here. So it's after tripping, it's closed, and we have a solid connection to ground. It's a one-shot device, so the idea is you are changing this once you have it's earthed. So the fault happened, you are going to site, you are first of all have to locate the fault. I think, Paul, we will see this also later on another video. We will locate the fault, maybe isolate the defective device, remove the rat which was, let's say, walking around in the switchboard, and then change the 3 primary switching elements. They should be mounted somewhere it's easy to access, and also to change, and then we turn live again. So we are back with this system in few hours, let's say, depending how fast people are on site again, compared to days and maybe weeks if you have really damage and you have to wait on repair works and you have to wait on material. Very quickly, what we are covering full medium voltage, so up to 40.5 kV. We're having, let's say, 50K, 63K medium voltage, as well as 100K in low voltage. This principle for sure works also on low voltage. Summarizing, last slide, what is again the summary? We have definitely, let's say, safety and protection as one key value, as well as the continuous operation, which is very important, that we are really, when time is money, we are very fast again back in service. And as well, it's very easy to install. You see on the picture, we have actually here the kit which is available for our partners if they would like to install it loose in capacitor application, which we are talking today, but also loose in other application or also conventional switchgear. We are covering not only the loose part for sure as ABB, we are also offering this in our new ABB switchgear as option. We're also having it available as a retrofit for sure as option, because this is also great to really upgrade existing switchboards or existing applications where maybe they are working very fine, it's no problem, but they are having just, let's say, maybe not the highest standard in arc safety. And then we can use this also as retrofit. As I said, we are covering full, medium, low voltage. We are compatible. The detection, I went, let's say, just briefly through detection. We are working with very well proven ABB technology like TVOC from low voltage, or our REA protection relays from a medium voltage, which are very optimized for light detection. We are, for instance, marine certified, and as well as UL recognized as loose product. So that was it exactly from my side. So hopefully not too long, not too many slides, and let's move on with maybe some more interaction here.
Yeah. So I'll ask a question because nobody else is asking questions, and don't forget in the chat box, ask questions. We got the experts on with us. So is there a watchdog type device or a self-monitoring device so you know this thing is operational when it's sitting in your switchgear?
Yeah, we are having actually, we are really designed the device with a long experience of let's say short circuit devices. We are coming from the IS limiter, the fault current limiter in the market since the 60s. Which is also, let's say, it's doing the opposite. It's fast turning off. It's another target application. So a lot of, let's say, knowledge of it has to work when it has to, let's say, stay there ready and then it has to work once when it's really important. And this knowledge, first of all, has came in. And then also we have done, let's say, a lot of, we have the testing, we have a test mode, for instance, we have a ready signal. This signal is then also can be given, let's say, to a next level communication, that we are able to if something is not okay with the primary switching element, that we have an alarm saying, okay, we have to check it, and so on. So this is also there. We have, as I said, a test mode where we can, let's say, go to test mode, because, well, as ABB or as a salesperson in ABB, I'm loving to have UFES units tripped, but I mean, the thing is, you cannot just trip it for testing it, then you have to exchange the 3 primary switching elements. So we have a test block where we can simulate ready tripping, ready primary switching elements. We then can give light signals. We have a test mode, so we can really also if you do the maintenance, which is depending, I would say, also on the environment. If you have a very dirty environment, I would recommend that you do regular maintenance. You have to maybe clean the lens sensors anyway. So then, if you want to do a check, this is definitely possible. Yeah, to not trip the 3 primary switching elements and shut everything down. Yes.
And we're going to show a little bit of that testing in our facility in a couple of videos. So I'm going to bring up a promotional video that you have that actually does a testing in the switchgear, and I think it shows very well how this system works. So, and Martin, you can speak over the top of this video as you go.
Sure. We have here, what we have done is we took now the classic application, as you said, Paul. We have the medium voltage switch. You see here two panel arrangement, and you see on the left bottom cable compartment we have UFES installed, which is quite an elegant way. We have it installed in the cable compartment. It depends where you install it. It depends on the protection zone you need, but this is a very often chosen way. On the other side of the switchboard, we have actually done what we are doing. Actually, when we do an internal arc test, we are made, let's say, the artificial fault. As you see here, we just had this initiation wire, so we cut this insulation of the bus bars and we made the initiation wire. And then we have here the light sensors installed. We normally use in a switchboard 1 light sensor per compartment, so 3 light sensors per panel. And then you have it here, so the disaster is ready, let's say, in the switchboard. We're going now for an internal arc test, and this is 50 kA, which is quite at the upper level. Now the video is gone, but it's 50 kA. On the left hand side, 100 milliseconds, on the right hand side, 4 milliseconds. The 4 milliseconds is very boring. What you have seen as well is these indicators. We have not seen the switchgear because the switchgear is, let's say, we have some indicators around the switchgear, which is standard procedure in internal arc tests. So these indicators, like I've cut them, they are not allowed to catch fire, and that's why they are there. So if they catch fire, the test is not passed. And what I just said, we had the 100 milliseconds, which means it's a tenth of a normal switchgear rating. The switchgear rating, what we are having Unigear is actually 1 second, yeah. But now we are back here. You see here the damage in the 100 millisecond panel. So again, a tenth of the duration the switchgear can handle. The switchgear can handle 1 second. So imagine how it looks like if 1 second is done. So everything is gone. And with the UFES, you see there are some traces. Yes, you see, but the compartment is perfectly fine. You still have, and you see the thing in a second. You still see the initiation wire is still there, and this is really impressive. So you can really clean away the fault. We actually had an application once, a real tripping of UFES, and the customer came to us and said, "Look, it has wrongly tripped." Because there were no traces. And then we looked at the records, and then we see it has perfectly worked, but it was just so fast that actually there were no traces. So it's a benefit to have point light sensors if you have a very distributed system, because then you know where to look at. Because the point light sensor is showing you where it is, where the fault was.
Yeah. So I'm going to, Martin, I'll slide along. This is that switchgear without UFES. And you can see a lot of a lot of damage to the equipment. It would no doubt need replacement.
It need replacement, Paul,
yeah.
but we have to say the test would have been passed. So an internal arc, a passive internal arc test, would have been passed with this.
That's because it's arc resistant gear, or?
This is arc resistant gear. This is Unigear arc resistant gear, capable of doing 1 second.
Okay, so it passes the test, but yet significant amount of damage.
And this is the point which we see in many applications or many discussions as well. We are saying, look, but it's passive protected. Yes, it's passive protected, but you have to change that gear. And you are happy or lucky, let's say, if it's still an active product. If it's an old gear, which is not active anymore, or something like, you have to, first of all, to find a replacement and so on. And this takes time. So, and imagine you are in an application where it's hard to get the gear out. On a cruise ship, for instance. Yes,
well, and time. There's if this is in an industrial facility, a process type plant that's producing copper, you lost a switchgear and you lost production. And we have a question. Hey, we have a question, so
we have a question.
Yes,
let's see.
Great. So there's a couple questions perhaps here. Okay, so we got. Prasanna asked the question, what maximum short circuit rating is available for these earthing switches?
The maximum what we have is actually in the medium voltage is 63K. So it's actually able to carry 1 second 63K. So you have to manage to find a breaker upstream to interrupt the 63K in less than 1 second, let's say. And we are up to 100K in low voltage. So in 1.4 kV, let's say, low voltage application, we are also covering low voltage up to 100K. Yeah.
And I think the impulse level for this device is 150. Is that the max impulse level? 34.5 basically is what we're talking about here. I think it goes up to 150 kVBIL.
The maximum we're covering full 40.5 kV rated, means up to 200.
200. Okay.
200, we need this mainly in the Asian region, maybe in China. There we have, let's say, quite high, let's say, requirements on BIL, yes.
Yeah, and actually, I might note behind me is a picture of a project in Peru, and it's at high altitude, and that was a 200 kV BIL project for which we used this ultra-fast earthing switch. Yeah, so that's an example of a piece of equipment that if you were to have a fault, it would fail the filter bank, and it would potentially shut the mine down. So having the ultra-fast earthing switch in that project was desirable because they're wanting to protect not only the people that operate the equipment, but also the equipment itself, because it's vital to the operation of the mine.
I think on your, as you see in the application behind, I mean, you are again far away from like the public area and so on. And this is like the safety thing is from that perspective not that important. It's more the operational thing. Nevertheless, let me point out one thing. I mean, what we have seen before was a passive internal arc test. In the passive internal arc test, let's say the doors are all closed. Everything is like in closed mode. The key point is that the ultra-fast earthing system or ultra-fast earthing switch system is always on. It's also on when the door is open. So if you are at site, and there is, again, as I said in the beginning, there is the risk of human errors, and you are at site, you open the door. I mean, I think this, if you're talking arc-proof design, if you open the door, the passive arc-proven design is actually not helping you anymore, because then the door is open, and when you enter, then you have it's not really it's not helping you. So UFES is also on then, and UFES is also protecting you in case you are at site and you have open doors.
Okay, so another question: is it reliable? Can you reliably detect arcing faults, high resistance faults within 4 milliseconds?
Yes, I mean the point is, yeah, we really extensively tested this thing, and we also have done customer events in where we had let's say an arc in front of people, first an arc with some glasses, and that took them down. We had the UFES on. So we are really trusting the thing that it's doing its job. And as I said, we also had already some, let's say, successful interruptions. An internal arc should be a rare case, let's say, and but it happened, and we also had really systems out. We are now in the market since 2010 with it. So we have some applications worldwide installed, quite many around the world in different segments. And it happened as well that we really had, let's say, cases, and it worked always as it should. Yeah.
Okay. Okay, so when an arc is detected and you have a high current, do all the PSEs operate, or is it just one phase within that has the high current?
Good point. What we are doing is we are doing a three-phase fault, because the background is that normally in a medium voltage application, a switchgear, or also I think in a capacitor bank application, you have the arc starts at one phase. It starts somewhere, but normally it's a non-segregated system. So you have the bus bars beside, and there is no segregation between. So we do expect, or what we have seen also, is that we have, let's say, the arcing starting at one phase, but then normally commutates through a three-phase fault. So we have then the three-phase fault anyway. So we have a three-phase fault, which then will be, let's say, interrupted by a three-phase failure. Yes, a three-phase bolted connection. Yeah, we are not making phase-wise tripping with the ultra-fast reversing switch. Yes.
Okay. All right. So we have another question here. Can the UFES be installed on other manufacturers' switchgear? Yes,
it can. It can. It depends in these situations always who is doing it. I mean, we from ABB can do it. Sometimes also if it's your own manufacturer, for instance, like you, Paul, it's not a switchboard, but it's your application in a capacitor bank. I mean, you can as partner buy the loose component and install it for sure. I mean, we have different solutions. We have like we have a truck-mounted version, for instance, if it's maybe a very new switchboard, and you don't want to, let's say, maybe open the switchgear and add something, so you can like rack in, rack out, so have a very clear interface if it's a new switchboard and maybe the owner don't want to lose the warranty. But if it's an older equipment, we have retrofit solutions, and also, again, as I said, for partners, they are installing it also loose in their own device to offer a differentiation as well. Yes.
So I might add to this a little bit to your answer. So first, it's a very easy device to install. Up to Martin's right, to right of him is the three power switching elements.
Yeah, exactly.
They install in a very tight area. In fact, they can replace a bus support insulator. I mean, they're that small. Mm-hmm. So the system is very easy to install. So I would say as a retrofit option is very easy to install. You have to install a relay in the panel somewhere, cut out the panel, install. You have to put a transfer trip in, and you have to run the fiber optics. But all very well possible by a company that's a panel builder, for instance. Mm-hmm. From our custom standpoint, the custom gear standpoint, we produce cap banks and filter banks. Oftentimes you think of arc flash mitigation, you think about switchgear. But the reality is that arc flash hazard mitigation and this active arc flash mitigation system should be installed in a lot of other components like rectifiers, like the drive systems. These devices are all very expensive. They can be $500,000, $1 million each or more, and critical to operations. So having the ability to detect an arc and to eliminate the equipment damage, I think is very important. So I think it should be something that should be looked at for other components outside of switchgear and even outside cap banks and filter banks, but anything that's electrical, that's critical to a process.
Yeah, exactly. I mean, this is perfect. Yeah, that's it. Yeah. I mean, it's not. We are always as ABB for sure driven by the switchgear, since we are also very big provider of switchgear. But you're absolutely right. What you have done and achieved in capacitor bank application, and we'll have a look later. I mean, it's great, and this is exactly it. It's protecting the quite expensive equipment which is, and yeah, and there's a lot of energy as well in those systems, right, in the capacitor banks. So if, as we have seen in the very beginning, what can happen with the door. Yes.
Yes. So we're going to go on to the next video, because I think it's an interesting video, because it's actually it takes place in a transformer, dry type transformer. So it's another good one.
Yeah, this is a good one actually. We have here, and this is also an example how easy it is to really increase the safety of with the ultra-fast earthing switch. We have here, you see we have a transformer cubicle where we have a dry type transformer in. So we have the UFES electronic, it's the QL1 here, which has 9 light inputs, point light inputs. So it's perfectly designed can be used for such an application. So you have one small electronic and everything is in there. So you can connect the current transformers, you can connect the light sensors, and you have just one box, and it's actually quite simple. So you have here the transformer box, and you find the right, as you see again here, the indicators is a position to verify if there is any problem. And then you really have the internal arc. I think you also see it in a second. It was also initiated. So we have a leakage current of 31.5 K. And here we are at 300 milliseconds. So 3 times the duration of the fault before. We see it, yeah, here we see they've done, I think, there, the initiation wire, yes. So here as well, yeah. And then you see how it looks like in slow motion as well, in real time.
So I want to stop here for a second, Martin. So this is, maybe you just explain what's going on there. This is the test lab, the transformers inside that cotton box,
exactly.
Right? So maybe we want
this
to
is,
talk
yeah,
about that
the transformers in the box. We have these, let's say, these indicators, these cotton indicators around, from the side and from the front. So everything is closed, and the idea is to test. Normally, with this you test the enclosure. So if you test here for a certain amount of time, and then no of these indicators catch fire, you are safe for this amount of time. So the enclosure can handle this amount of current and for this amount of time. Yes. So the aim is always that nothing catches fire outside, and then you have this lateral, front, left, right. Let's say these different classes, which is then available. Yeah.
Yeah, I think that cotton wall that you see there, it's less than a meter, like a 0.3 meters away from the front of the enclosure of that transformer, right? So it's
tough to pass. There should not. Yeah, you should be. This is the thing of arc-proof design. Let's say you should be able to stand in front, and if then something happens, you are not getting the hot gases and the let's say the hot gases to you. And this is the thing. But again, the door is closed, so this is the topic. Yeah.
Yeah. So I'm gonna hit play again and
finish. Do this. So you see also we have here the pressure on the chart. So you see it in real life and then in slow motion what happens. So at the bottom is without, at the top is without, and at the bottom is with UFES. You see for sure also the pressure, which is then also, let's say, causing damage. You know, what you have seen in the other video, which is damaging really the panel is let's say immense if you have such a let's say without UFES, and with UFES for sure you are very limited. So this is with UFES, initiation wire there, so some traces, but it's still there. And we have without the UFES for sure this is different. We have here a lot of dust, dirt, so it's probably hard to clean here. So we have to do really maintenance, exchange parts, and you see also your damage of the pressure. Exactly.
So it's obvious here. I mean, the situation is that the transformer could have failed. You might have to replace the transformer. The transformer windings might have been damaged, but with having that ultra-fast earthing switch in there, perhaps you would have saved the transformer. Say it could have been a faulty lightning arrestor inside the transformer housing, for instance, a bad termination could have went right, and you would have collateral damage. So a lot of things that unrelated to the transformer failure that could result in the transformer being damaged and having to replace it. So we got some more questions. Next question is, would you expect the UFES to prevent the operation of the bus differential relay by locally causing its associated breaker to operate first? So in other words, is the differential protection faster than the transfer trip associated with the UFES?
I mean, the point is, yeah, this is a tricky one. The thing is that, first of all, how do differential protection really, let's say, act on interrupts the fault? If it's using a circuit breaker, we are by far faster. Because the thing is, what we are measuring, what we are looking at, we are looking at current, real current flowing, and light. And we are doing this, we are looking at light and current in less than 2.5 milliseconds, the first 2.5 milliseconds. It may be that there is some protection, like differential protection or something, who is also seeing that in that fast time. But if it's reacting with a circuit breaker, this is taking another 80 milliseconds. So that's why I think in this situation, not what we are, if we are a circuit breaker. What I mentioned when I had the single line on is, I mean, we can give the tripping signal from the electronic also to the circuit breaker. This was optional, because normally you have let's say, anyway, relays and protection system and maybe differential protection on. So this is then deciding which breaker to operate. But this is, we are not interfering with that. We have an independent system just looking on light and current. And then we are shutting down the whole thing. The only product which is in that speed, let's say faster, is down here. And this is an IS limiter or FC protector, which is on the upper corner. This is a product which is designed to operate before the first peak current. So this is like a fuse, a powerful fuse. So it's like a medium voltage fuse, which is with a rated current of 4,000 amps. So this is faster. But this is, let's say, we are talking about really now about two, let's say, short circuit specialized product. So, but if a circuit breaker is involved, it's actually not, I will not see that this is really interfering. It is needed to have the circuit breaker, actually, because this is interrupting the current at the end.
I might add something too. If
Please.
It's a question regarding, say, coordination and trying to limit the extent of the fault. The reality is a three-phase bolted fault, which is what, in the end, this UFES system creates a three-phase bolted fault. You're bringing that bus voltage down to zero. And whatever is connected on that main bus switchgear line up and downstream from there will see 0 volts and it will trip offline. So the reality is that you're trying to prevent damage. You're going to have a shutdown in your loads, and you may, whether you trip those other breakers or not in the differential zone, it really doesn't matter, because all the load will drop off because of because of an interruption. So.
No, absolutely, yeah.
Yeah. So John, you're not allowed to ask questions. John Stechik's asking questions. He says, how many devices can you protect with one set of PSEs?
A very good one. Thanks, John, for that. Actually, it really normally, as you've seen before in the single line, normally you think, okay, you need per feeder one UFES system. When we look into the UFES and how to design the system, and I think, Paul, you know it very well from your capacitor banks, you have to define the protection zone first. What do you have, what amount of feeders, or what part of the switchboard, or the total switchboard, if it's a bigger one, we would like to protect. And then it depends on it. On simple switchboards, one incomer, or you have like on a simple capacitor bank solution, you have maybe one incomer, and then you have the system. So then you have, maybe you install the primary switching elements just very close to the incomer, maybe in the cable compartment of the incomer. And then you have one system. You can have, let's say with the REA protection relay, let's say you have really a lot of flexibility. We have point light sensors, we have ring light sensors. if you would like to have, let's say, an area more protected with a ring light sensor, which is great. Ring light sensors, you can send some test signal if the ring is fine. Point light sensor have the benefit that you know where it happened, because you know where it was. And with the TVOC, in opposite, you can connect up to 159 point light sensors. So this is equal, when you go back to switchgear, to 51 panels, actually. So 159 compartments. Or even, no, 53, I mean. So 53 panels. So this is the beginning. But normally, if you have like 2 incomers, you have maybe a more complex system. We are going maybe to 2 systems. We had one case now just recently installed where we had a customer 30 panels, 23 UFES systems. He put them really in the outgoing feeders, and to have a very selective tripping, to just isolate the area where the fault is. So normally I can say we are talking 1 to 2 systems, maybe 3, but then it's already a big switchgear. Or if you are then want to have it very selective, then you can for sure go up. There is actually no limits, normally 1, 2. And with light sensors, we have enough. We can connect to one system up to 150 point light sensors. So there is no limitation to that.
So since we're on this, I'll take a moment just to show you a very large system. The one behind us, I have the actual drawing for that, and I'm going to put up on the screen for a moment.
This will be interesting, because
yes.
How many have you used there? Because this is already, it's very big.
Yes, so that's a very big system. So in this one, I'm just going to list off the parts. We had our QRU 100, we had a REA 101, and then we had multiple REA 107, so up to 1, 2, 3, 4. And I think each one of those REA 107s had 1, 2, 3, 4, 5, 6 light sensors on it. So on this project we had 1, 2, 3, 4. So we had 24, a total of 24 light sensors, point sensors on that. So that's a very large, a very large system. But the system's scalable is the point. And
absolutely, yeah.
Yeah.
And this is a very large system, and I think if you just can go back, you have it. I think you have the PSCs in the entry, right? In the really the incomer, right? At the here.
Yes, they're at the incoming of the system. Yeah, right
you
here
have
actually.
Yeah, exactly there, exactly. And maybe I haven't highlighted this. We have the QRU 100 is the electronic which is compatible with REA with the REA family. The QRU 1 is compatible with the TVOC. And here it is like REA. This is really a great product as well, since we are having here a lot of options, as you said. We can extend it normally as far as you really want it. We can put the ring light sensor module in, and you can also make it selective. You can say, look, if it's happening in that area, I don't want UFES to trip. Or in that area, I would like just that the tiebreaker is opening. So you have a lot of options. You can tune your system.
Yeah. So anyways, the project behind me is well over $1 million, and to put in a UFES system makes a lot of sense. We got another question that came in, and it's... Is the UFES CSA approved, is the question, and do you need any special CSA inspection to install UFES in Canada?
This is actually something I'm not 100% sure. So here I would use my phone choke and Chanzu, because
Chanzu, you're on.
I don't know if she's on, but Chanzu, you're doing Canada, so you know this.
Yes. Well, yeah, you need to get it CSA certified. So the question is, CSA is needed. The answer. We have a couple of installations in Canada, though. Sometimes it's enough to just to provide the UL certification we have. But generally speaking, we just do CSA certification project specifically.
Yeah, so I'm going to add to this, Kansu. So we ship projects into Canada, and what we do is we get field certification. We have a field inspector come in and inspect the system, and they'll put that CSA tag on the equipment once it's been field certified, or in fact, they come down to our factory and they check out everything. They make sure we apply it within the ABB recommendations, and then it becomes something that can be operated in their system. Does that mean that the system is arc flash resistant, certified arc flash resistant gear? No, it does not. It doesn't mean that, but they will approve it to be installed on their system and operate on their system.
Yeah.
So, thanks a lot.
Yes.
You're welcome.
Douglas has a question. Douglas Strang. It says, please clarify that ultimately the UFES is depending on an upstream OCPD to open. Must be a power circuit breaker, maybe. Is that clearing time not determined of the arc flash energy in the subject equipment? Do you get the question? I could maybe reword. I think I understand it.
Yeah, I mean, not entirely. So
yeah. So the question is the UFES system ultimately requires an upstream breaker to clear, because the UFES system is creating a three-phase bolted fault. You have an arcing fault condition. The UFES system picks it up within 4 milliseconds. It shorts out that arc, right? And then it relies upon an upstream system to clear. So I think I'll answer the question, Martin, if you don't mind. So during the period of time that you have an arc shown, that's when you have heat and pressure buildup. The heat and the pressure buildup is from the arcing event. In 4 milliseconds, Martin, correct me if I'm wrong, the PSE will shunt out that arc and the arc will disappear. Why? Because there's a zero impedance shunt around the arc and you eliminated the arc. And basically we're distributing the energy back into the source impedance rather than into the enclosure through the arcing, the heat associated with the arc. So it's not really dependent upon the upstream breaker. If the upstream breaker were to fail and say we had to go to a backup breaker and it were to extend, the piece of equipment that the UFES was in would still be saved because the arc has been eliminated from that gear.
Yes.
Would you agree with that?
Yes. Absolutely. This is the thing. And maybe to add one point, yes, we need a breaker to interrupt the current. And as you said, Paul, it could be the first upstream breaker, or if this failed, it could be the next one. But we should take this into account when we design the protection zone. Let's assume we have seen it in your application, in your big gear. You have the UFES really in the entry, where I guess the cable come in with all the energy, and then you have your capacitor bank. So you really have it at the beginning. So the question is, what do you have prior to the UFES, looking when the energy comes in? Is there a breaker in your gear, or is there just a cable coming? And if a cable is coming, you have to ask yourself, if you design the switchboard, I think with the customer, what happens if UFES is tripping? Is there on the other side a breaker? Is this breaker my breaker, or is this a utility breaker? We had some applications where the customer said, I don't want that my utility has to trip, because if they trip, they send me a check. So then we can look into this and redesign and put the UFES on a different position. To put it really at the entry is maximizing the protection zone, because if you put it somewhere in your gear, you have from the energy entry to the UFES, there is no protection, because if there is an arc, you will not shut it down, right? This is the thing. So we always have to consider the protection zone, and then also really discuss this in the application. I mean, I don't know how you have done it in this big gear, which is behind you, how this was maybe a topic, and yeah, exactly. So
to me, putting it on the incoming makes the most sense, because then
it makes the most sense. You reduce the stress. I mean, to be also clear, what we also face, maybe this question will also pop up later on, is this three-phase bolted failure. Isn't that a huge stress for the equipment? Yes, it is. It is. It's not a simple thing. But also to highlight, I mean, also if you put it in the entry, then you protect, I mean, you don't have to stress in the entire system. You have it just at the entry point, then it's there. But also if you put it somewhere else, if you put it more in the middle or maybe in a switchboard at the bus bar, switchgear are tested for that. There are short time current tests, and they are 3 seconds, and the switchgear can handle the test, the current in that way. And sometimes also the transformer should be able to handle it. There is no big difference between a internal arc current and a UFES solid 3-phase to ground current. It's a bit higher because the resistance has to be a bit smaller, because otherwise the current will not commutate to the UFES.
Okay, we have more questions. You're not getting off too easy here. Grant Connors asked the question, is the UFES device resettable? Question, there's more to it. Or is it a one-shot device which requires replacement upon fault? And if the UFES can be reset, can you please explain the process of resetting it?
It's a one-shot device. So the primary switching element, well, the electronic for sure not, but the primary switching element is a one-shot device. I've seen before we are using, let's say, the microgas generator in the airbag, and this is similar. I mean, like the airbag, it's also one shot, let's say. So the idea is, okay, you have a fault, you go to site. First of all, you have to, not be in a hurry. Even though you have a very expensive production, you have to first of all see what really happened. So you are investigating, you are disconnecting in a concentrated way, maybe the faulty compartment, you are cleaning, you are checking what really happened. Then you are changing the 3 primary switching on, it's plug and play, and you can just reset the electronic and it's ready again, because it's only ready if it has 3 ready charges of microgas generators there, and then you're good to go.
Okay, and another one from Chris McAndrew. Could the UFES be used on a system with fuses as the primary overcurrent protected device? The UFES will essentially crowbar the fuses till they clear.
Yeah, this is a good one. I think here we really need to, because it depends also on the type of fuse and so on. This we really have to investigate. We have such applications, or we also did some investigations. So we are somehow, what I think Chris is asking is, he has in mind that to have the UFES in and then the fuse is clearing the fault.
Yeah, I think I almost feel like he's
fast then, right?
Almost similar to maybe the IS limiter, maybe, or no? Or
the IS limiter is going in a very similar direction, and knowing that product, which is first of all doing the opposite, turning fast off and then on, and there we have the fuse in parallel. And knowing this, and this is from an engineering point of view a different league, let's say, because here it really matters which fuse we are using. We have a dedicated fuse engineering case by case. And with this background, I cannot give a very straight answer to that. We really have to look into this. So Chris, always welcome. Text us, call us in ABB, and we will look into it definitely.
Okay, all right. So I'm going to play video 4, and this is actually from our factory floor. And so, okay, everyone, I'm out here in the shop to show you how to use it. And you turn up the volume. Closed cap banks. Pete is out here today actually doing a virtual FAT with some folks in Quebec. This is a C-high pass harmonic filter system going up into northern Quebec, so it's an Arctic rated device. So Pete, why don't you just talk about the UFES system, how it works, how it's installed in our gear for the audience.
All right. So, why don't we start here?
Okay.
All right, with the primary switching elements. All right, so the UFES system starts with the primary switching elements. These are the devices that will put a direct short onto the bus bars if the system detects a fault with light and current. So on here we have 3 connections. They are disconnected right now. Those are the cables that will activate these 3 primary switching elements. On the back side, there's a large ground bus that will ground the fault current, and on the high side here, that's connected directly to this, would be connected directly to the source cables. We have our primary side for the switching elements, and so if a fault is detected, the internal of this bottle will basically short out like a switch to the ground bus, and it'll extinguish any arc that takes place. So those 3 cables come around to the front of the equipment, come back to the enclosure, and they feed into the back of the relay here, PSE1, PSE2, and PSE3. So with this, we have optical sensors. Right, and for this project, we have a total of 8 optical sensors out of 9 being used. These optical sensors are located in the various compartments. We have 2 sensors located in the incoming isolation compartment, source compartment. We have 2 located in the breaker compartment. You can see one right there, maybe, and another one over here. And then we have 4 located in the main reactor and capacitor compartment. And these optical sensors, they can kind of, they're kind of like an eye, so they look in all directions, in the direction that they're facing. So,
Pete, do you do an overlap on the sensors? So it's an overlap.
yeah, we always do 2, so they're kind of overlapping one another.
Okay.
And then we expect quite a bit of reflection also inside during an arc. So I mean, I think it's during an arc period, it's going to be pretty bright in there.
Can you talk about what you do for testing, how the testing process works when you're at the factory?
For testing, we just got, we basically have just a little small test instrument. We connect this to the equipment. This basically defines what basically it's like connecting the bottles up during normal operation. So we're basically just taking out the relay, telling the relay that the bottles are actually connected, but they're not connected. So that's what this device is doing. They're connected to the primary switching element rather than have the actual device being set up where you could actually possibly false operate those elements. So setting up the relay itself is quite simple. It's all done with dip switches. There's no program required. There's trip conditions, and there's for trip conditions, we generally use there's light and current. We generally use both light and current for switching. We want to make sure that there is some current flow before we actually trip. We normally set that just above what our nominal current rating of our bank would be, so that the bank has to be on, basically. And then with that current, we also would require to see light, and with the 2 conditions, the primary elements can actually switch. So you can also just do light only as an option. So I mean, that's an option. So that's the setup with the dip switches. There's other extensions, extension 1, 2, 3, 4, and 5. If you had multiple other light sources that are through a relay, you can send those additional inputs into these extensions.
Would it be like a 751A, for example, aux? Or
it has to be something that sends out a signal that would be able to be read by this.
Okay.
We have not used it for these options here, 2, 3, 4, and 5. And then for trip current, basically it's just dip switches. It's kind of like a binary. We normally set it on the lower side. So for our project here, the trip current is 1.5 amps times IR, where IR is a 5 amp secondary CT. So we're tripping at 1.5 amps times 5 for our trip current.
So this key does what? What's this key do?
This key, if you can put it in test mode. We're in operation mode because we're using the test instrument in the back. But if you didn't have the test instrument in the back, and you're saying you're testing the equipment, you would always want to put that in test mode because you wouldn't want to necessarily activate those bottles under test mode.
Okay. All right. So yeah, why don't you go through how we test? Do a sample test.
So for testing, what we're going to do is we'll just close the circuit breaker. So now the circuit, you can see you heard the circuit breaker close. we generally will input a current into the bank here. So we have a current injection going into the bank, and so the relay has to see both current and light. So right now the bank is seeing current, and if we want to now activate a light source, we can just do that with a flashlight, and I'm going to go in and just activate, basically put it up to the source here, and there was a fault inside the breaker compartment. And the neat part about this is you can see the light sensor number 3 picked up, so you know where the fault took place.
So in the end, if this was a real short circuit condition, the power switching elements would have brought the bus bars to ground. It would have resulted in a transfer trip to the upstream breaker, as well as this breaker here.
Yes.
And to put the system back in operation, you'd have to purchase 3 more switching elements,
Yes.
install those,
Yes.
and you'd be good to go. But the assumption here is that the fault current is significantly reduced, the time duration is significantly reduced, and therefore the damage is significantly reduced. And incidentally, this is an important piece of equipment. It's expensive. So the purpose is to reduce damage and also improve the safety for workers that work around the equipment. Anything else, Pete, to add?
No, that's it. Pretty simple.
All right. Well, back to the shop. Back to the back to the office. All right. Well, so you guys met Pete, by the way, before, but Pete's a twin brother. So.
Yeah, it was hard to. Who is who? Yeah.
I'm better looking.
Oh yeah.
I think we're just about towards the end of the presentation. Oh, I was going to ask you the questions because Pete was stuttering a little bit on it. Extensions 1 through 4. What are they used for? Why don't you tell us a little bit about those extensions 1 through 4 in the back? Looks like they maybe connect on the back. There's extensions 1 through 4. Maybe they attach to other light sensing devices.
Yeah, I think we have some. If I'm not very familiar with the wiring in detail, but this was a QRU1, so this has 5 inputs for TVOC2 extensions. So if you need more light sensors, and I think these extensions you mean are just let's say tripping signals, which can be, there is also, let's say, you can there's some externally trip signal which you can give, if I'm right. So both electronics, like QRU1 and QRU100, have the ability to have, let's say, some external trip, which we sometimes also investigate if we have, let's say, potential customers who would like, oh, okay, I have another relay. Can I use this with the UFES system? So we have some options, also some input outputs, which gives us a bit more flexibility than just working with the ABB relays. Yes. Timing is always key, so we always have to look into this in detail because it really depends what signal we get then, because it has to be really quick and clear as well. Yes.
Okay. All right, so I'm gonna go to a conclusion slide just for a moment, Martin. I'll be back with you in a second. All right. Okay, so in conclusion, today the PDH code is 993. Email paul.sedgwick@nepsi.com, or if you received emails from Matt, you can email matt.marcet@nepsi.com. Just don't email both of us, otherwise we'll be sending you 2 contact hour certificates. In terms of today's conclusions, the UFES system is a very effective way to improve the safety with electrical equipment and is also very well suited for custom power equipment. NEPSI's equipment is custom, right? Metal closed cap banks and filter banks, but also consider them for VFD drives, rectifiers, motor housing, things like that. I think it would be also very well suited for those types of places also. Very easy to install. We've done it many, many times now. The systems work great. It's relatively inexpensive, especially if you start factoring in the cost of the equipment and the cost of downtime, and then also the cost of life should somebody get hurt. So the litigation costs and so on. So there's are a lot of other costs to factor in. Our recommendation is that you strongly consider this active arc flash mitigation system, and it reduces the possibility of catastrophic failure of equipment. It reduces the downtime. It protects your investment. From an OEM standpoint, from NEPSI standpoint, we are sometimes asked to provide 2-year, 3-year warranties. From our standpoint, the UFES system is great when the customer purchases it because it limits our liability, because if there is some type of failure within the equipment, a component failure or some other type of failure, even if it's from a rattlesnake, the amount of damage that occurs is significantly less. Sometimes it's just a dust it off, blow it off kind of thing, replace the failed component, put it back into operation. The process is back up and running very quickly. So it protects also your people, your operational people. And let's face it, sometimes they make mistakes. They may not be well trained, or in the desire to get a plant up and operational again, they may start working on equipment live when they should not. So our recommendation is to also consider their health and safety also. So Martin, back with you. I do appreciate your time. I think we have no questions. So
everything answered. Very good.
Yes. Do we have your contact information handy? I guess I should talk. In the United States, we work with Costas, and Costas has been on the air before. And then I think I can flip back to my original slide. Yep, the original slide. I'll pop it on for a second. Right there beneath my head there is Martin.
Yeah, there is my mail address. Yeah.
Yep, at de.abb.com. You can always contact him. They have product literature on their website and things like that. Anyways, I appreciate you coming on today. It's been fun.
Thanks a lot, Paul, for having me. It was really a pleasure and a very interesting session. Thanks a lot.
Great. All right. We'll see you. Thank you.